the main difference between doing a multi-object system and a single object system is that with the multi-object system, you need a free body diagram for each object. So there will be more than one free body diagram and therefore more than one set of X and Y force equations. So we'll write our force equations or our problem solving procedure over here and just to remind ourselves of it, and then we'll work a problem. Step 1 is draw free body diagrams. So we have one per object. Include all external forces. This is also if the two blocks are touching each other, you have to include the forces between the blocks because it would be external on each block. So we'll say even between the blocks. Because if we have, say, one block that's sitting on the ground, then if we draw the free body diagram of that block, we know that we have the weight, mg, and we have the normal force from the ground pushing up on that block. Now, if we have a second block sitting on top of that one, then our free body diagrams are going to look a little bit different. So the free body diagram for the white block will have, we'll say MWG for the white one, and then N1 from the ground. And then pushing on it from the other block will be MRG. Now, instead of writing that as MRG, because honestly, we could even have a third block on top of that. So we will write that a little bit differently, and we will call this force N2 for the second normal force. So that normal force will be in between the red block and the white block. So if we have normal force 2 pushing down, then that means that on this red block, we will also have an equal and opposite force into pushing up. And then we will have the force from the blue block, and we'll call this one N3, pushing down there. And then if we draw the free body diagram of the blue block, then, oh, we forgot to include the weight of this one. So MRG for the red. And then finally on the blue block, we've got the normal force 3, that equal and opposite force coming up from the red block, and then we've got the weight of the blue block. We'll say that's MBG. Okay, so you have to include all the forces in between the blocks. Okay, so let's actually work this out sort of as an example. So if we've got a weight for each block, so we'll say that if we're given mass of the white block equals 20 kilograms, mass of the red block equals 10 kilograms, and then mass of the blue block equals 5 kilograms, we need to find normal force on N1 on the white. And then we'll also need to find normal force 2 between the red and white, and then normal force 3 between the red and the blue. So we've already got the free body diagram for each block, so that's convenient. So here we just need to assign a coordinate frame, and because we'll just assign y in the vertical direction and x going to the right. So we'll say x goes to the side and y goes up. Let's see. We can also check, just for fun, let's add a force here. And we'll say we've got a pushing force P. And we'll say P to move blocks. And in that case, then we also need to be given the static friction. We'll say static friction is 0.5, and we'll say that that's the same for all, like all the surfaces have the same static friction. So we get friction here, friction here, friction here. Let's go ahead and we'll finish out the solution procedure. So step 2 is assign a coordinate frame. If you have a rope going on, X needs to follow the rope. So we'll say X in the direction of motion, Y perpendicular. And if you have a rope, which we don't on these, but we'll do in another example, then X follows rope. That would be like if the blocks were at different orientations relative to each other. 3 is write equations. And we need to write those equations now for each block. So we'll have sum of the forces Y equals M Y double dot, usually equals 0. Sum of the forces in X equals M X double dot, may or may not be 0. And then finally, 4, we solve the equations. So here we need to solve for all the normal forces, then P, and then A. Let's start here with the blue block because that one's the one on the top. That'll be the easiest one to solve for. So basically, we're going to sum the forces in the Y direction for every single block, and then work out the normal forces. Now, because we said here that there is friction, then there would also be friction forces if these blocks are moving together. And we'll have to know if these blocks are moving together or not. So the blue and the red block are not going to be moving separately. The blue and the red for sure will stay together because there are no sideways forces pointing on those two. The white block may or may not move with the other two. And that is a situation like, if it depends on how much the friction is compared to the weight of the blocks and compared to the force P. So somebody could either push so hard on P, like say you hit the white block with a baseball bat. You have a really high force for a really short period of time, and that could make the white block just scoot out from under the other two, and then the red and the blue would just fall down. Or if you pushed it more slowly, then all 3 blocks would move together. So really what happens is going to totally depend. So we know that this white block is going to try to move. P is obviously trying to push the white block to the right. So that means that the friction from the ground is going to be pushing to the left. And we'll call this friction 1 because it corresponds to normal force 1. So that friction is going to be pushing to the left. And as P is trying to make this white block move, that also means that the friction from the red block on the white block is going to be pushing to the left as well, because these have to oppose that force P. So we'll say here F2. And then here we'll have P. So now here on the red block, this friction, it's the same friction between the two blocks. So because these are like reaction forces, then the friction between red and white on the red block has to point in the opposite direction. So we will push that to the right. Call that F2. So we know that's the case because if you think about the white block trying to move out from underneath the red block, then that's going to be smearing to the right. And so that's why we have that F2 going to the right. And we know that the blue block is not going to move off of the red block because there are no sideways forces between the blue and the red. So there really we shouldn't really need to bother with any friction on there because we know that the blue and the red block are going to have to move as a single unit. Let's start out with the blue block. Sum of the forces in Y equals 0. So normal force 3 equals M3 times gravity. So that means that normal force 3 equals 5 times 9.81, and that equals 49.05 newtons. Okay, so N3 equals 49 newtons. Now for the red block, things get a little bit more complicated here. We know that a sum of the forces in the Y direction equals 0. And here we have going up, normal force 2. Going down, we have normal force 3 and M red times gravity. So now we can solve for normal force 2. And normal force 2 equals normal force 3 plus mass of the red block times gravity. So this is going to be the 49.05 plus 10 times 9.81. And that is going to equal about 147 newtons is normal force 2. So if normal force 2 is 147 newtons, then we can find friction force 2. And Fs on 2 equals mu s times N2 equals 0.5 times that 147 equals 73.5 newtons. Okay, so the normal force 2 between equals 147. We've got that answer. And the static friction force there is 73.5 newtons. So then finally, we need to do the forces on the white block. So we'll have sum of the forces in Y equals 0. And this is going to equal normal force 1. Pointing up, we get that from here. And then pointing down, we have minus normal force 2 minus mass of the white block times gravity. So this tells us that normal force from 1 equals normal force from 2 plus mass of the white block times gravity. And so that's going to be 147 plus 20 times 9.81, 343.2 newtons equals normal force 1. So here, this happens to be the same as the weight of all the blocks. which that should be, right? Because all the blocks are sitting on the ground, therefore the normal force from the ground should be equal to the weight of the blocks, because we didn't have any other vertical forces going on there. Now we can find the friction force 1. Okay, so friction force 1 equals mu s times normal force 1. So we just divide 343.2 times 0.5, and that equals 171.6 newtons is friction force 1. So now to see what P is going to make the blocks move, we'll do sum of the forces in X. And sum of the forces in X is mass times acceleration. But here we're trying to find the balance point. What's the minimum P required to make these blocks move? So what quite overcomes static friction? And so we're going to say 0 here because we're going to just barely overcome that static friction. And that will be going to the right, we have P. Going to the left, we have F1 and F2. So P equals F1 plus F2 equals 171.6 plus our F2 we got over here 73.5. And so P equals 245.1 newtons. So this is the force required to make the blocks move. So next we have to figure out what is their acceleration. Well, in order to know their acceleration, we have to know dynamic friction. So let's just put in a dynamic friction, maybe say mu d equals 0.4. As long as it's less than 0.5, that's a reasonable amount, but you will be given that. Okay, so for the dynamic friction, then we're basically going to have the same sum of the forces in X equation, except instead of equaling 0, it'll equal mass times acceleration. And then instead of static frictions, we'll have dynamic friction. So let's push this down a little bit, and then we will have more space to write that. So we need to be able to figure out the dynamic friction now for everything. So switch back to red. And so dynamic friction is going to equal the 0.4 times that 147 instead of 0.5 equals 58.8 newtons. So that's dynamic friction for 2. And then we need the dynamic friction for 1. So to say that there is F1S. And then we're going to have F1D equals mu D times N1 equals the normal force, which was this 343, times 0.4. And this is going to equal 137 newtons. So now we have sum of the forces in the X direction equals mass times acceleration. And this mass is the mass of the white block, only the mass of the white block. Peter has a question. If the red box will move along with the white box anyway, since it's on top of it, why do we need to add both forces of friction? That's an interesting question. So we got to actually figure out if both of the blocks, if all the blocks move together. So if all the blocks move together, then it only matters the friction force on the bottom, because we would be treating all the blocks as a single unit moving together. If we treat just the white block moving, then in that case, if just the white block is moving, then we would need to include the frictions on both of them. So let's scroll back up and look at it. Okay. So if just the white block is moving, then we have to account for F2 and F1 both. If all the blocks are moving as one giant lump, then we would only include F1. So I think what's happening, if P is this that we calculated, this P I think would make the white block scoot out from underneath the red block. If P is less than that, then it would make the whole blocks move together. I think that's how it would go. So yeah, I think in this example, the white blocks will slide out from underneath those two because of how hard it's being hit. And we could calculate, so the force to make these blocks move together, then in that case, we would have to treat it, and I'm gonna just come to make a different color here. So if we wanted all the blocks to move together, then we would treat it as something like this. So we have all those masses, we have this normal force, we have friction force 1, and then P would be just need to be greater than friction force 1, which in that case would be P needs to be greater than what we get for friction 1, like 171. I think if P is less than 171.6, nothing's going to move. If P is greater than 171.6 newtons, but less than 245.1 newtons, then all the blocks move together. Or if P is 245.1 or more, then just the white block would move. That's my theory.